to design approximation algorithm using a procedure called rounding. Okay, and we saw how deterministic rounding was done. We then introduced one of the possibly cornerstone concepts in linear programming theory, which is LP duality. And using it, we found that instead of actually solving the LP, we can design what are called primal dual algorithms. And we looked at quite a few algorithms that fall into this framework. And I mentioned briefly that even known algorithms, combinatorial algorithms such as Dijkstra's shortest path algorithm, does indeed fall into this framework. Okay. Okay, so hello all and welcome back after a long break. As you might guess, the remaining lectures of this course, like this one and the other courses you'll be attending, will be conducted online. Now, it's kind of unclear what will work in this context, so we are all trying out different tools. If you have feedback on how the lecture is, or how the lectures are going on, or you have suggestions for improving either interaction online or improving the quality of the stream lectures, please post it on Piazza. It will be really helpful to improve this as we go along. Okay, so it's been a long break, so let me kind of give you a wrap-up summary of the course until now. So here's what we have seen. We started with designing approximation algorithms using purely combinatorial techniques. Okay, so the nice cute example of this was the TSP algorithm that we saw, which gave a 3/2 approximation. Okay. Then we moved on to what are called polynomial time approximation schemes, fully polynomial time approximation schemes, where you get a 1 plus epsilon approximation to the ideal solution. Then we introduced this really powerful framework of linear programming. Now, linear programming has got wide applicability beyond just designing approximation algorithms, so it's always a useful tool to know. In our case, for our purposes, we used it to design approximation algorithm using a procedure called rounding. Okay, and we saw how deterministic rounding was done. We then introduced one of the possibly cornerstone concepts in linear programming theory, which is LP duality. And using it, we found that instead of actually solving the LP, we can design what are called primal dual algorithms. And we looked at quite a few algorithms that fall into this framework. And I mentioned briefly that even known algorithms, combinatorial algorithms such as Dijkstra's shortest path algorithm, does indeed fall into this framework. Okay. Okay, so I hope that kind of refreshes you with a very bird's eye view of what we have done. We'll continue with this framework of using linear programs. But what we are going to move on to in this next unit is to look at randomized, what you've seen before, or they're not going to be significant in the rest of designing better algorithms. Now, here's a small operational note regarding how evaluation will be conducted once the on March 19th. So that will get postponed to at least a week from now. The topics, of course, will remain the same. I will not include randomized algorithms in that. Okay. So this will be given either as an online or a take-home one. Okay, so just wait for details on that. Please keep checking the Piazza page for details. Okay. So that being said, let's move on to today's lecture. Okay, so let's begin with the very basic of how would one define a randomized approximation algorithm. Okay, so in a randomized algorithm, or in particular for randomized approximation algorithm, the algorithm is allowed to toss random coins. Okay, and how many random coins? By random coins, I mean just you can think of it as a 0-1 variable, which is 1 with a certain probability p and 0 with probability 1 minus p. Okay. So it's allowed to toss around a poly number of them. Again, it's polynomial in the input size. Okay, and the actual execution of the algo will proceed depending on the outcome of these coins. Okay, so for instance, if the coin toss, suppose you are tossing 4 random coins, and the toss outcomes are something like head, head, tail, tail, then the algorithm will do something. If the toss outcomes are head, tail, then the algorithm will do something else, and so on. Okay, but given the outcome of the tosses, the algorithm is completely deterministic. So, okay, so it is possible that on some tosses, the algorithm might err. Okay, that is basically the fraction of tosses that on which the algorithm outputs an unexpected or a bad answer in some sense. Okay. Okay, so what do I mean by a bad answer over here? Well, if the algorithm, I expect that the algorithm for a minimization problem is less than alpha times opt, then a bad outcome is basically that the algorithmic value is greater than alpha times opt. Okay, so the number of tosses or the fraction of tosses on which you actually get a bad output value is going to be small. Okay. So we'll formalize this by saying probability over the random coin tosses is less than equal to gamma. Okay. Now you might ask, what exactly is gamma? Like, is it 2/3, is it 1/3, is it 0.001? How bad do you want the error probability to be? Well, typically when you're looking at approximation algorithms, the value of gamma will something, we can target a gamma, as we'll see, of something like 1 over n squared. Okay. But while designing an algorithm, actually it is sufficient to get something like any constant. Okay, and we'll see that using some sort of error amplification tool, we can actually get the probability of the bad outcomes to be down to 1 over n squared. Okay, or 1 over n cubed, or 1 over poly n in general. Okay, okay, so that's kind of the definition or the informal definition of it. So let's give a formal definition. Okay. Okay. So a randomized alpha approximation algorithm for a minimization problem. Now, an analogous definition holds for a maximization problem, so I'll just leave it to you to think about what it will be. Okay, it's almost trivial. So, okay, so what is it? Well, as input, it takes 2 parameters. Usually for an approximation algorithm, you'll just have the input instance I, but this algorithm will also take error probability delta. Okay, and the output, so notice that delta can be anything as such, and as you have seen, the ideal delta that we'll hope for is something like 1 over poly n. So what is the output that we want? Well, the algorithm will toss some random coins, and finally what it wants is that the probability that the cost of the algorithm on I is greater than alpha times opt of I. So this kind of the bad event is less than equal to delta. Okay. So this is kind of the approximation guarantee that we are hoping for. Okay. Now, of course, this again should hold for all instances. Okay. And I would like to emphasize that the probability over here is over the outcomes of the random coin. Now notice over here that I have not really told you anything about, there should be a trade-off somewhere, right? Because you can't hold this for all inputs delta without there being a trade-off in terms of delta. Well, the trade-off as expected will come in terms of the running time. Okay, so we'll write it as the algorithm runs in time. Well, a usual algorithm will run in time polynomial of n. You're also allowed an overhead of polylog 1 over delta. Okay, by polylog I mean something like it could be log raised to 5 and so on. Sorry, it's just messing up the writing towards the edges. Okay, so in general it's polylog is log raised to a constant. So you can immediately note that as the delta goes to 0, let me just fix this in a moment. Okay, so as I was telling, as delta tends to 0, the running time, as you can see, is allowed to go to infinity. Okay, so this is the most general version, and as I said, if you're looking for an inverse polynomial error, the running time remains polynomial. Okay, so we'll usually make our algorithms run with an error probability of 1 over n squared. As we'll see, actually even that is not required. What we will do in fact is use the following operational definition, which states that all we want is that the expected cost of the algorithm is less than alpha times opt. Okay, and we'll see that actually as long as we use we ensure this inequality, it implies the formal definition. Okay, and we'll see this in a moment as to how this happens. Okay, so I hope this is clear, and now we'll go on to the example of max cut. Okay, so at this point I would like to emphasize again, as I did for the probability in the formal definition, that the expected value over here is over the random coin tosses. Okay, over the outcomes in that. So the algorithm does toss some random coins and it comes up with different costs, but in expectation the cost of the algorithm solution will be at most alpha times opt. Okay. So if you wanted a similar maximization problem definition for the same, you'll have that the expected cost of the algorithm is greater than equal to the approximation factor times opt. Okay, so that's just analogous. So with that in mind, let's move on to our first example of a randomized approximation algorithm, which is MaxCut. MaxCut is kind of our favorite problem through this course. We'll come back to it again. Okay, now the input and output, I hope by now is very clear to all of you. The input is graph with weights on the edges. Okay, which are all non-negative. The output is a cut SS bar, and what we are looking at is to maximize the weight of the edges out of S. Okay, S complement. What is this weight? Okay, and we want this to be as large as possible. There's a really simple randomized algorithm for this. We saw a local search algorithm. We saw a deterministic rounding algorithm, unless I'm wrong. And let's just look at a randomized approximation algorithm for this. The approximation algorithm itself is really trivial. And as stated, it has got nothing to do with LPs. Okay, so you go over each of the vertices, toss a coin, which I'll denote by a random variable xv. Okay, where xv is equal to 1 with probability half and 0 with probability half. Okay, so you just look at every vertex, independently toss a coin for it, which if it comes up heads, put V in S. Okay, it's just as simple as this. Let us try to analyze this algorithm. I think many of you might have already seen this. If yes, just bear with me. So we want to analyze the value of the cut. What we're going to use is linearity of expectation. Okay? And this is going to be one of the main tools. So as and when we use probability tool, I will highlight them. Okay. So the probability tool that we're using is the following, that given any t random variables, z1 to zt, okay, each of them follow some distribution, and in fact they need not be independent. The expected value of the sum is equal to the sum of the expected values. Okay, now this is a really powerful tool, mainly because the random variables need not be independent. Okay, so I think in the survey most of you had said you know this, so I won't go into the details of it. So let's see how do we use this to analyze the algorithm. What is the probability that a single edge is cut? This is simply the probability that xu is not equal to xv. Now xu and xv are independent random variables. Each comes up to be equal to 0 or 1 with probability half. So the probability that they are unequal is exactly equal to half. Okay. Now let us define new indicator random variables. ZUV for each edge UV in E. Okay, and as expected, because they indicate a random variable, ZUV is equal to 1 if UV is in the cut. Okay, and by being in the cut you mean XU not equal to XV and 0 otherwise. Okay. So now let us try to analyze the expected cost of the algorithm. So this is simple enough. The cost of the algorithm for any single outcome of the random coins is simply summation over the edges in the graph of WUV times ZUV. Okay, so it adds up the weights of the edges that participate in the cut, that is when XU and XV are different. Okay. So what does this give us? Okay, so just have a look at the definition again. Okay, so this gives us that the cost of the algorithm is actually the expected cost is equal to summation UV E and this is by linearity of expectation. Okay, and if you have seen some probability, you will be aware that this is exactly equal to the probability that ZUV equal to 1, which is the probability that XU is not equal to XV, right? And this we know is equal to half. Okay. So what you have gotten is an algorithm that gives us an expected cost which is at least half times the total weight of the edges, which hence is at least half times opt. And therefore what we have gotten according to our operational definition is a half approximation for max cut. Okay. Okay, so I hope the algorithm is clear. Let's just go over this once more, just the algorithm itself. All we did was the randomized algorithm was almost trivial. We just included a vertex into our target set S randomly with probability half. Okay. And the key fact that is used in the analysis is linearity of expectation. Yeah. That is the sum of our random variables is equal to sum of the expectation of the sum of our non-independent random variables is in fact equal to the sum of the expectation of them. Okay, so now make a slight detour to ask the following question. This was a randomized. And the question to ask is, why does finding an approximation guarantee just in terms of the expectation sufficient? Okay, and why does it become equivalent in terms of polynomial time equivalence to our earlier formal definition? Um, Before I show why it is sufficient, it might be the probability that cost of alpha phi is this equal to alpha times opt of phi is less than equal to delta, okay, for some target delta that is given as part of the input. And the probability and the expectations are over the random coin tosses of the algorithm. So we'll go over a small exercise in probability to show that this implies this. Okay, so here's a basic inequality in probability that was also part of your problem set. So this is called as Markov's inequality, and we mentioned that most of you know about this, so let me just go over this first. If x is a non-negative random variable, then the probability that x is greater than or equal to a is less than or equal to expected value of x divided by a. Okay, and this holds for all a. Okay, that is of course non-zero and greater than 0. Okay, so let's use this now to show what we want. Now using Markov's inequality immediately gives us so you take x to be the cost of the algorithm on input I. Note that this is a random variable simply because for every random coin toss the cost that the algorithm outputs changes, okay, or might change. So you get that the probability that the cost algorithm, in fact now onwards let me just drop this the input I because that's going to be kind of obvious. The probability that the cost is greater than, and let me say this is 1.001 times alpha times opt of I is less than equal to expected value of cost of L divided by alpha times opt of I times 1.001, right? Scroll this up, and this is less than equal to 1 over 1.001. Okay, because I substitute expected value of cost of algo phi, I upper bound it by alpha times opt of I. Okay, now this is some constant, right? And let me call this as gamma. Oops, sorry about that. Okay, and what is happening here is our bad event, say. So we are not going to give an exact alpha factor approximation, but we are going to give an alpha times some number really close to 1. So it's something like an alpha plus epsilon factor approximation. Okay, you can make this 1.001, as we'll see, as small as you want. So now let's use this. Now what we wanted ideally was this to be gamma. Sorry, delta. Okay. So how do we reduce it to delta? Well, use something called as amplification. Okay. So the idea is that you do a random coin toss and you run the algorithm on the basis the probability of a bad event is upper bounded by gamma, right? So now what we'll do is the following. You run the algorithm R times. Okay, so you repeat it some capital R times. Each time the probability of a bad event is less than or equal to gamma. Okay, so this is what happens. Oops. Okay. But notice that what I can do is if I run the algorithm R times, I have R different outcomes, right? And I can choose the best outcome out of them. Okay, and what do I mean by the best outcome? If it is a minimization problem, as it is in this case, choose the solution out of the R that has the best cost. Okay, or rather R runs, okay, that has the best cost. Now, why does this help? Well, the probability, getting back to what we had, probability that the run number T gave a bad outcome was less than or equal to gamma, and this holds for all T. So that all runs give bad outcomes is less than or equal to gamma raised to R. Now what have I used here? I have used another implicit probability tool that if you have R independent runs, then the probability can be multiplied. Okay. Okay. That is the probability that first is bad and second is bad and so on is less than or equal to gamma raised to R. Okay, so that's what I've done over here. Now notice that this is the really bad event. If I choose the best outcome of them and the best is bad, that corresponds to all the runs giving bad outcomes. Okay. So now what we wanted is we have done it R times. Okay. And we want the overall bad event to be at most delta. Then you choose R so that gamma raised to R looks like delta, rather is equal to delta. And this implies that the number of times you run the algorithm looks something like log 1 over delta divided by log 1 over gamma. Okay, notice that delta, gamma are less than 1, so that's why this thing makes sense. Okay, so what we have done is just repeat it and chosen the best outcome. We have run the algorithm R times. And all of a sudden we have our desired result. Now, what have we lost in this process? Of course, we have lost in terms of the running time. Okay? The error probability has come down to delta. Okay, the approximation factor is almost the same. That is, as we had seen, it's something like say 1.001 times alpha. Okay, the running time though is now something like r times the original running time. Okay, and what is r times the original running time? Well, r is log 1 over delta divided by log 1 over gamma. So if my original running time to produce an expected cost of at most alpha times opt is poly of n, and that is usually the algorithms that we come up with, then this is something like log 1 over delta divided by log 1 over gamma times poly of n. Notice that this thing here is a constant. So this whole thing is poly of n times, in fact there's not even a polylog, it's just log of 1 over delta. So that is why usually in most of the algorithms that we see from now on, when you're talking about randomized approximations to them, we will bound the expected cost of the solution produced by the algorithm. Okay. Okay. So small point, the constant here, if you remember, just clarity's sake, was something like 0, 1. Okay, so if you want to keep the running time polynomial, you can, this is the same constant that is over here. Okay, now this can be made, notice that because we are trading it off in the approximation factor, you can make it something like say 1 plus 1 over n cubed or something as an overhead to alpha, while still keeping the running time polynomial. Okay, so this is just again an exercise in probability to verify that this is true. It's not really useful for us. Okay, so I hope this is clear as to what we're doing. Let's go on to actually designing randomized algorithms for rounding linear programming solutions. Okay, we have seen only deterministic versions of rounding until now. What we'll see next is how to round set cover. Now, you will see in a moment that the algorithm, the kind of guarantee that it gives is slightly different from the exact formal definition that we have said over here. Okay. And it's easy enough to note what the difference is, but I will tell you beforehand, before I start writing out the LP as a note. So you assume that the algorithm always outputs a valid solution for each coin toss. So in case of say vertex cover, you do something randomized and you output a solution that is a subset of vertices that is always a vertex cover irrespective of the coin toss. Now this may be relaxed, as we will see. So the kind of guarantee that we want is that the probability that the algorithm outputs a valid answer and cost of alg is less than or equal to alpha times opt is bounded by delta. And this is the kind of guarantee that will give in set cover. An order log n approximation will go based on randomized rounding. Okay, again, as you might notice, this is not really useful. We have already seen an exact log n approximation using deterministic techniques, that is a greedy algorithm. And in fact, I think also using a deterministic rounding scheme, unless I'm wrong. No, we just saw F factor approximation using that. So randomized rounding will give us this order log n. Okay. So I'll keep this guarantee on top. And let's try to write out and recall the LP relaxation for set cover. I'm not going to define the problem in too many words. You've got sets S1 to Sm, and you've got elements which I'm labeling as E1 to En. You've got M sets and elements and output a subset of the indices of 1 to M such that Si, or rather I've been using J for this, covers all of the elements in U. Okay. Objective, in fact, let's take a weighted version of this, a weight function which goes from the set of sets from E is J to okay, so set Sj has a weight Wj. Okay. So what is the LP relaxation for this? Something you have seen many times over by now. Your objective is to minimize over J in M Wj x Sj. Okay, where xsj is supposed to be the indicator of whether Sj is in the set cover or not. This is subject to the following constraints for each I in n, or rather let me write it Ei in U. You have summation over J such that Ei element of 0 and 1 for all J in M. Okay. So I hope the LP relaxation for set cover is clear. Let's go on to rounding this. Okay, so our rounding algorithm is going to take the following view of the variables. Of course, the first step, unlike our primal dual algorithms, because this is a rounding algorithm, we actually will be solving the LP. So solve the LP and get the optimal solution. Used again x Sj stars for J in M. Okay, so this is our optimal solution and it has value ZLP. Okay. Now the key is to actually interpret the XSJs as the probability that Sj is in the set cover. Okay, so since these numbers are bounded between 0 and 1, each of the XSJs, this is kind of a natural interpretation to assign to the variables. That is, the LP is kind of guiding you and telling you that, look, this set Sj, if it's like 0.7, kind of there's a good chance that it is indeed in the set cover. Okay. So how do you use this now? So beyond this, the algorithm is kind of what you would expect. Okay, so because XSJ is the probability that Sj is in the set cover, what we are going to do, we are allowed randomness, is to toss a few random coins. Okay, particularly we are going to toss at the start one random coin for each Sj. So toss a coin xj, which is takes the value 1 with probability xxj, and 0 again with probability 1 minus xsj. Okay, and of course these are stars, so I'll leave the stars over there. Okay, and if this coin comes up heads, then you add j to your candidate final set cover. Okay. And then of course at the end you output I. So great, so we are finding a set of indices using this procedure, and we are outputting a candidate set cover. Now of course, like before, we have two things to verify, and the first is I always a set cover? Okay. And notice that right off the bat this might not be true. And this is simply true, say for instance, suppose all the coins that you toss came up 0. What do you do? Okay, so this is something that we'll have to analyze, and we'll put this on hold for a moment as to how to fix this. This is kind of the bad news in some sense. The good news, on the other hand, is that what is the expected value of the cost of I? Okay, and the cost in this case is the weight of I. Well, it is just the sum over j and m of wj times xj. Okay, because xj is 1 when j is included in the set cover, so of course the quantity here is the actual value of this output I, the weight of the output collection, and you have an expected value over that because each of the xj's are random variables. Now this, by linearity of expectation, is summation j in m wj expected value of xj, right? And what is the expected value of xj? It is just x sj star. Okay, and I'm just using the fact here that the expected value of a 0, 1 random variable is just the probability that the random variable is 1. So I hope you all are familiar with this. So good. This is kind of the good news side of things. Okay. And why is this good news? Because notice that this is exactly equal to ZLP. Okay, so I would just wanted that the expected cost is somewhere some alpha close to the ZLP or alpha close to the opt. We are in fact getting the expected cost to be exactly equal to ZLP. Okay. So now what happens, or what we'll do is we'll try to fix the bad news in some way, okay, to make that to be to make I to be a viable set cover, and while doing that we are going to lose out in this approximation factor. So how do we fix the bad news? I is set cover. Okay. And we'll see what does this turn out to be. Well, consider a single element. Okay, rather I call it EI. Okay, and what is the probability that EI is covered in our cover? Okay, so its I may not be a set cover, but there's a certain probability that it covers a fixed element EI. Okay, and the probability is the following. Well, in fact, we are going to calculate it as the probability is not covered, right? And what does this turn out to be? Well, the probability that EI is not covered by I is the probability that none of the sets are chosen. Okay, and this is, since every set is chosen independently, this is exactly the probability, the pi over all j, such that I is an Sj and none of these Sj's are chosen. Okay, now what we can do is apply an inequality over here, our favorite inequality, 1 plus x is less than or equal to e raised to x, and this becomes xsj star. Okay, now this is useful. What is this exactly equal to? Well, this is just exponential this term here of minus summation j such that I element of Sj x Sj star. Okay, and this we know from our LP constraint. As it is feasible, the sum of these xsj stars that cover any given I is at least 1, right? So this is greater than or equal to e raised to minus 1, which is like 1 over e. Okay, so the probability that any given I is not covered is like 1 over e. So how can we get this probability down? Well, we are going to get this probability down. Okay, And we're going to reduce this probability by using something like amplification. Okay. So our modified algorithm is going to be the following. We just repeat the previous algorithm. Some 6 log n times. Okay, the 6 is kind of arbitrary. Anything greater than equal to 2 works. Okay. So for t equal to 1 to 6 ln n, you toss a random coin for each j, but now every random coin appears in this loop, so you've got xjt, which is 1 with probability xsj star, 0 probability 1 minus xsj star. Okay, if xjt is equal to 1, then you make union j. Okay, so you include sj in the set cover. So an sj is included as part of the final set cover if it turns out to be included in any one of these iterations. Okay, so I'm going to call the 6 log n to be equal to r for clarity. It's the number of times you repeat. Okay, and then finally, of course, you do the same, you output I. So let us try to analyze this modified algorithm in the same way as before. So we'll just introduce some notation. Let me use a different color for this. Let IT be the sets included in iteration number t. Okay, so now first thing, let us analyze what trade-off we achieved in terms of the good news before, that is the approximation guarantee. Okay, in terms of the approximation guarantee, we have that the expected value of the cost of the algorithm is equal to the expected value of the weight of the final output set, of course, but this is equal to, or it is at most equal to, in fact, let me just write it down as in a compact form. Okay, and now notice that I've been a little loose in terms of the definition here, because a set Sj can be added, say, in iteration 2 and can also turn up heads in iteration 3. In this case, you can as well include it because it's not going to play a part in our analysis as such. Okay, so these ITs might actually overlap with each other, but finally you are outputting the final union of all the sets that are included at any point during the iteration. In that case, we analyzed that this is less than or equal to ZLP. Okay, so the upper bound still holds whatever the definition of IT that you take. This, therefore, each of this is bounded by ZLP. So this is R times ZLP, which is 6 natural log of n times ZLP. Okay, good. So we have a 6 log n approximation if our I is a set cover. Well, okay. Now let's see this. How do we analyze this? Well, what is the probability like before? EI not covered in a single iteration, or rather in, say, a fixed theatre iteration, is we had seen 1 over E. Implies the probability of the bad event, that is EI, is not covered in any iteration is less than equal to 1 over e raised to r. Okay, and we have chosen r being 6 log n for a good reason, because now this probability turns out to be 1 over e raised to 6 log n, which looks like 1 over n raised to 6. Okay, and now we'll use a third probability tool, which is also going to prove extremely useful, which is the union bound. Now the union bound states the following: if E1 to EL are events, then the probability that E1, E2 or EL, that any one of them occur, is upper bounded by the sum of the individual probabilities. Okay, again, you don't need anything about the independence of these events. Okay. So we'll use this now to say that the probability that I is not a set cover is equal to the probability that there exists I such that EI is never covered. Now this, by the union bound, is at most n times 1 over n raised to 6, because there are n elements EI. N raised to 5. Okay, so with overwhelming probability, the output I is indeed a set cover. Okay. So we have a combination of kind of two events. The probability that the expected cost or rather I should say the expected cost, in fact I can say expected weight of I is surely less than equal to alpha times, or rather 6 log n times opt, and the probability that I is a set cover is greater than equal to 1 minus 1 over n raised to 5. Okay. Now how do I combine both of these into a statement that says that probability that weight of I is greater than equal to 6 log n and I is a set cover is greater than equal to, let's say, some 1 minus delta, where delta is the input given to you for the target error. Well, what we'll do is we'll just show, and this is just a two-step show, that weight of I is greater than, say, 10 ln n, and I is a set cover is greater than something like 4 over 10. Okay, and then you can use our very old amplification to get to delta cover. Okay. So at this point, this is completely operational in the sense that it is just an exercise in probability rather than introducing new concepts about approximation algorithms. So usually if you show something like this over here, that is the expected cost is bounded and that the probability that the solution is valid is large, this is kind of the place where you'll stop in terms of designing an approximation algorithm. Okay. So let's quickly do this exercise in probability to show that how the two statements here imply this. Okay. Okay, so how do we start? Well, again, this just a few lines. Markov's inequality implies that the probability of weight of I greater than or equal to 10 log n is less than or equal to 6 ln n over 10 ln n is equal to 6 over 10. Okay. Implies the probability that weight of I greater than 10 ln n. Sorry, there was a typo over here. I missed something. This to be less than equal to. Okay. Here's the probability that weight of I greater than 10 ln n, or I is not a set cover. This is by the union bound less than or equal to 6 over 10 plus 1 over n raised to 5. Now you might note that this 1 over n raised to 5 is not really useful. You might as well have that to some constant. Which is less than or equal to 6 over 10 asymptotically. This is tiny, and this by complementing will give probability that weight of I is less than or equal to 10 ln n and I is a set cover is greater than or equal to 1 minus 6 over 10. Now this is small o of one term, so this is greater than small o of 1. So this kind of proves the form we want. Okay. So just to emphasize, this part here, if you reach to something like this, is usually enough. Okay, and beyond this is just like routine mundane probability stuff. Okay, but it has to be seen once so that you understand why statements like these two actually imply what we want finally in terms of a formal definition. Okay, so I'll stop here. It's been, I think, a little over an hour 10 minutes. So I'll take questions on Piazza if required, and we will see if we need to modify this format for the following lectures. Okay, in particular, if some more interaction is possible, that would be great, but there are issues with that also currently. So we'll work on that over the next few lectures. Okay, so again, please use Piazza to post your doubts. The notes will be up on Piazza by today evening. Okay. Okay, thank you. That's all for now. Bye.